Welcome everyone. In this lesson, we're going to continue to look at the different types of chemical reactions. This lesson, we're going to focus on what we call single replacement reactions, also known as single displacement reactions. And then we're going to take a look at what is called a combustion reaction. Let's start with a single replacement reaction first. This type of reaction is also what is classified as an oxidation reduction reaction. See, this reaction is driven by a transfer of electrons. And if you look, there are two general formulas written below. And what they both have in common is you could see that one element is replacing a similar element in a compound. What we mean by that is that a metal will replace a metal, or a non-metal will replace a non-metal. An analogy that I like to use is imagine that the metals are boys. Okay, and the non-metals are girls, and you have a couple dancing. If you look at the first example here, we have BX, where B is the metal and X is the non-metal. You could say boy-girl. And then you have an element by itself, which is represented by the letter A, trying to cut in. Now, A, being a metal, wants to replace the metal of BX. So A wants to replace B. In other words, the metal wants to replace the metal, or the boy wants to replace the boy and start dancing with the girl. Now, when that happens, notice that A will kick out B. So here's the new metal, the metal that just got kicked out. And then A and X start to dance, and you have your new couple dancing. The same thing can happen when a non-metal replaces a non-metal. Notice that Y, being a non-metal, Y wants to get together with B, okay, to form BX. The reason B is written before Y when they do get together is because in chemistry, the positive ion, which is the metal, is written first. So in the second example, the non-metal kicks out the other non-metal, which is X. So you can see that X is now by itself. And the non-metal and the metal get together. Just remember that the metal is written first as a standard rule. Now, in order for this to take place, this is one of the most important things about single replacement reactions. There's an activity series that we will refer to verify if this will happen or not. You see, the activity series has the more active elements at the top, and as you go down the list, the elements become less active. Now notice that hydrogen, which is with an asterisk here, is on the list. Now notice the list is divided into the metals on the left, and these are the non-metals, which are represented by these four halogens on the right. And the reason hydrogen is there is because hydrogen acts like a metal. Hydrogen usually is a +1 charge, and since it acts as a metal, it is part of the list. Now, the way you use the activity series is that the element that is trying to cut in has to be higher on the list than the element that it's trying to replace. And I'm going to show you how to use this list with the next few examples. The same thing happens with the nonmetals, which are on the right side here. By the way, notice fluorine, chlorine, bromine, and iodine, the order on the list happens to be the same order that they are on the periodic table. Fluorine is the most active nonmetal, and iodine would be the least active of the four. So let's take a look at some examples. Here are four particular examples. This first one, you got aluminum, is the one that's trying to cut in. So think of this iron 2 nitrate as a couple dancing. And what aluminum wants to do is aluminum wants to get together with nitrate. So aluminum wants to replace iron. So here's how the activity series works. Let's go back here for a moment. Let's clear this. And I want you to focus on the two elements from that example. Okay? So if you look here, aluminum is the one trying to cut in. So aluminum is right here, and it's trying to kick out or replace iron. Notice iron is down here. As long as aluminum, the one trying to cut in, is higher than the one that is currently in the compound, as long as this is the case, which it is, it will kick it out. It will proceed. So what's going to happen is aluminum will get together with nitrate, and then you got to know how to write the right formula. See, aluminum is +3, nitrate is -1. So when you crisscross, that's how you get this formula that you see here, aluminum nitrate. And then iron got kicked out. So you write iron as just simply Fe. Iron is not diatomic, so you write Fe. The rest of it was due to balancing. Okay, if you notice here, once this happens, there are 3 nitrogens there and only 2 over here. So the least common multiple is 6. So a 3 was placed here to make it 6 nitrogens. A 2 was placed here to also make it 6 nitrogens. And then what happens is by putting a 2 here, you got 2 aluminum, so you put a 2 over here. Since you put a 3 over here, you have 3 iron, so you put a 3 over here. And if you look at the oxygens, they're balanced already because you got 2 times 3 is 6, times 3 over here, that's 18. 3 times 3 over here is 9, times 2 here is 18, so everything's balanced. Okay? Now, I want to skip this second one for a minute. I'm going to put an asterisk. We'll do that one afterwards. Let's look at the third one. In this third one, magnesium is trying to cut in. Now, magnesium's a metal. Now, I know hydrogen is not a metal. Here's the couple dancing. But hydrogen acts as a metal. So magnesium wants to get together with chlorine, but the only way this is going to happen is if magnesium is higher on the list than chlorine. Let's go back to the list and let's take a look here. We'll erase these two. So magnesium is the one trying to cut in. Magnesium's way up here. Hydrogen is way down here. So this will happen, okay? As long as you're the higher one on the list, it will cut in. So when we go back to this problem, magnesium and chlorine will get together. Again, to write the correct formula, you need to find their charges, crisscross, and you get MgCl2. And then the balancing of this one was pretty easy. Since there's 2 hydrogens and 2 chlorines, you put a 2 here, and everything gets balanced. So that one wasn't too bad. Now, let me show you the fourth one here. This one's interesting because if you look, the one trying to cut in this time is a nonmetal. This would be an example of a nonmetal trying to replace a nonmetal, or a girl replacing a girl in my analogy. So the nonmetal wants to kick out the nonmetal here. So it wants to kick out Br, bromine. The nonmetal wants to get together with the metal. Now, again, we got to use the activity series. So let's go back and let's focus now on the right side. So the nonmetal in this example is chlorine. Chlorine is trying to replace bromine. And if you look, chlorine is higher on the list. So this will kick out Br. So when we go back and we look, you'll notice that chlorine will kick out the Br. But notice when Br got kicked out, this is why it's important to know your diatomic elements. Br is one of those elements that's found in nature as a diatomic. So you got to remember to put the little subscript 2. Now, chlorine and bromine are going to get together, but remember that the metal has to be written first. So when they get together, put the metal first, put chlorine second. Now notice what I'm about to do. The reason chlorine has a 2 over here is because it's diatomic. However, that rule does not apply once that element is going to get together with someone else. The minute that chlorine gets together with a metal, in this case potassium, drop that little 2. Notice I did not write the little 2. Find the charges of each, which is +1, -1. Crisscross, and you will get your KCl, which is what you see here. To balance, this one's pretty easy. Notice there's 2 Brs here, so that's why a 2 was written over here. And by putting a 2 here, you now have 2 potassiums. So if you put a 2 over here, not only do you fix the potassium, you also fix the chlorine. You have 2 on each side. So make sure if when you kick an element out, recognize if that element is diatomic or not. In this case, bromine, once it got kicked out, it's diatomic, so you had to put the little 2. Now I'm going to give myself a little bit of space here, and we're going to go ahead and we're going to look at the one I asked you to skip, which is the second one here, number 2. This one's a little tricky because this is a single replacement involving water. This is what I usually tell students to do. When you have a single replacement involving water, okay, I ask them to rewrite water as HOH, where the first H is the metal, it acts as a metal, and then you got OH as the nonmetal. Now, the person trying to cut in is sodium. We know sodium is a metal, so sodium wants to get together with OH. That means that sodium wants to kick out the hydrogen. We still got to go to our activity series. So let's go back over here. We'll erase these here from the previous example. Notice sodium is way up here, very active. Hydrogen is way down here. So because sodium is much higher on the list, it will kick out the hydrogen. This will take place. So sodium is going to get together with OH. OH is acting as the nonmetal. So again, you're going to find their charges. When you crisscross them, that's how you get NaOH. Now notice that hydrogen got kicked out. Hydrogen, like earlier with bromine, when hydrogen gets kicked out, it's diatomic. So you must put the little 2. Once you do that, then you just got to make sure to balance. And what happened here is, if you put a 2 here, and you put a 2 here to balance the sodiums, notice you now have 2 oxygens, and there's 2 hydrogens here, but 2 more over here. There's 4 hydrogens in total. If you put a 2 here in front of the water, you fix everything. You now have 4 hydrogens on both sides and 2 oxygens on both sides. But the trick here is when you have a single replacement involving water, you should probably write it as HOH to make it more visual. Treat the first H as the metal, and then the OH is what's actually acting as the nonmetal in this example. Now, you might see an example where, and I'll give myself a little bit of space here. Let's say, and I'll write one here for practice. Let's say you have copper, and I'll do it over here. Copper reacting with, let's say, potassium fluoride, okay? And first you got to recognize, all right, is copper a metal or a non-metal, right? A boy or a girl? Well, the metal, which is what copper is, metals want to get together with the non-metals, okay? So copper wants to kick out potassium. Metals replace metals. So when you go back to the list over here, okay, remember that copper's trying to cut in. Look where copper is. Copper's over here. He's trying to cut in. So look where potassium is. Potassium is one of the highest ones, one of the most active ones. Look what happens. When the one that's trying to cut in this example, it's copper, when it's lower than the one that we're trying to replace, which is the K over here, it's not going to replace it. This is the reason we need the activity series. What's going to happen is copper will not kick out potassium. It will not get together with fluorine. So nothing is going to happen, so you can simply write no reaction. That's an abbreviation for no reaction. So whenever you have an example where the one trying to cut in is lower on the activity series than the one it's trying to replace, nothing will happen and you will write no reaction. Now keep in mind, what drives these are transfers of electrons. These are oxidation reduction reactions. However, we must consult the activity series anytime we're doing a single replacement reactions to see if it will occur or if it won't, like you saw in this last example. Okay? Now, another type of oxidation reduction reaction that we're going to look at is called a combustion. Okay? The ability of a compound or anything to undergo combustion, that's a chemical property. And notice that I'm going to show you three general formulas for combustions. I wrote two of them over here. These are the most popular ones. One of the most classic combustions is when you have a hydrocarbon. And I put CXHY because it could be pretty much any combination. It could be C2H6. It could be C6H6. It could be C4H8. Let me go ahead and fix that. So C4H8. It could be many different combinations. So I just put XY there for the C and for the H. Now, notice that when you have a combustion, what they all have in common is that the other reactant, and this is probably the key, when you see oxygen in the reactants in its elemental form, which is diatomic, we're going to classify these as combustions. Oxygen is what's going to fuel the fire. It's what's going to generate and allow this reaction to burn. Now, it is an oxidation reaction. There will be a transfer of electrons taking place. And when hydrocarbons burn, you will always make, as your products, carbon dioxide and water. All combustions involving these hydrocarbons will do that. Now, the second example is the same thing, except in the first example, I used a hydrocarbon for obvious reasons. You can see it's just hydrogen and carbon. But the second example is a sugar. A sugar can burn in a similar fashion. And what I'll do is let me erase here, and I'll put, I also put X, Y, and Z here. But it could be any combination. I don't know if you remember from biology days, but sugars are usually a 1:2:1 ratio of carbon to hydrogen to oxygen. One of the most popular ones is glucose. Notice the ratio here. So any sugar has this 1:2:1 ratio, and when it burns in the presence of oxygen, you will generate carbon dioxide and water. So this is another example of these types of combustions. Okay. Now I'm going to show you one more example that follows the same pattern. You might have an alcohol. And alcohol can also burn. And the general formula of an alcohol would look something like this: CXHY. And alcohols have this functional group called OH. So it'll look something like this. But again, you'll notice this is what they all have in common. They all have that oxygen as a reactant. And this one will also generate carbon dioxide and water. So if you burn a hydrocarbon, a sugar, or an alcohol, notice that these generally make carbon dioxide and water. Now, I am going to show you one other thing here. We saw earlier, if you look here, you can have a reaction such as CuO, copper 2 oxide, plus oxygen. Okay, and actually, let me write it like this. Let me make it a synthesis. You can have copper and oxygen getting together to form copper 2 oxide. Okay, I'm going to write one more here. You can put aluminum getting together with oxygen, forming aluminum oxide. And normally, when you look at this, you immediately think, oh, this is a synthesis. And you are absolutely correct. This is a synthesis because we are putting two elements together. In a synthesis, there's only one product. So these are definitely classified as synthesis. But this actually has a dual classification. You can classify this in two ways. You can call it a synthesis, but you can also call it a combustion. And I'm going to explain to you why these can be classified in multiple ways. You see, combustions, no matter what, oxygen, this is the key, is one of the reactants. Again, oxygen in its elemental diatomic form. Okay? So when oxygen is by itself as a diatomic molecule, and you see it in the reactants, not in the products, in the reactants, you can classify that as a combustion. Again, this one obviously you would have to balance, to make it completely correct at the end. Here you would put a 3 here, a 2 here, and then you'd put a 4 here. But If you were asked what type of reaction this is and you answered either synthesis, combustion, or both, all of those choices are correct. Okay? So single replacement and combustion, as well as synthesis and decomposition, which we've seen before, those four types of chemical reactions are all driven by one thing, by a transfer of electrons. They are all what we call oxidation reduction reactions. Okay? In the next lesson, what we'll take a look is at double replacements or double displacements. So this lesson the focus was on single replacement as well as combustion.